Well, I'm glad to see that the room is quite full. It's, I guess, good to give a talk on the first day. And now that you're still fresh and clear, or maybe tired from traveling. Anyways, I'm going to talk about a quantum cloning game with applications to quantum position verification. And this work was done together with Leo Collison, he's in Grenoble, and Florian Spielman, who is in Amsterdam. Very well. Just like as a quick outlook, I'm going to define a game, the quantum cloning game, study it, some properties and blah, 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 study its parallel repetition, and then give application to quantum position verification into like models. Okay, that's it. A game and then applications. First, if we think of a game, a non-local game, a standard quantum one, we might think of a referee and two parties that are not at the same location. They are just spatially separated. And then like these parties are gonna be like have quantum power. So that's why I put an atom on the computers that they hold. So quantum computers. And then they usually share some quantum resources. Let's say that they prepare a quantum state that I name it rho, okay? So the referee, she does is the following, picks questions, namely X and Y, and then sends them to Alice and Bob respectively. According to a certain predicate, they can do whatever, but they have to get some outputs, A and B, and if they fulfill a certain relation, they win. If they don't, they lose. So like the most famous example of such a game is the CHSH game, where the outputs, if you XOR them, they have to be equal to the product of the inputs, okay? But there's like some things beyond this standard non-local game scenario, and I can give you some other examples. And the first one is the quantum XOR games, where you have a quantum question instead of here X and Y being some classical things, and you have to output something classical. You also have another scenario that is rank one quantum games, where you give the two players a quantum question and they have to produce a quantum state as an answer. And there's like another example that I came up with, or I just found, I didn't come up with that. It's like quantum referee that sends classical questions to the players and they have to answer with classical answers, okay? So with that, I want to move forward and introduce the game that is the following one, quantum cloning game. And in this presentation, I'm going to use the following notation. The 5 plus is going to be the maximum entangled state, EPR, the 0, 0 plus 1, 1. And in this game, we have the scenario that we had before, and now I'm going to restrict to the case where the referee picks a bit. And the thing is that they're going to share a quantum state, but not only Alice and Bob, the players, but the referee is going to have a part of it. And the referee is going to hold a qubit of a tripartite state. So this state is prepared by Alice and Bob, and the referee has a qubit of it. And the following goal is what defines the game. If they receive X, at the very end of the game, the referee and Alice have to end up with a maximal entangled state. If, on the contrary, they receive the bit 1, it has to be the referee and Bob who share a maximal entangled state. So it's like, from my point of view, kind of a natural game. It's like I'm gonna be the referee, and either you and I have to end up with a maximal entangled state, or you and I. And the thing is that, okay, let's see if the players, like preparing strategy whatsoever, how well they can perform, okay? And so what is the strategy? So a strategy is to prepare a quantum state. And the thing is that you have a referee system that is fixed, so that's a qubit. And then they can have any, like Alice and Bob, Hilbert spaces that they want. And upon receiving the questions, they can act locally on the state. So, and the most general things that they can do are CPTP maps, or just perform quantum channels. And they end up with a quantum state at the very end. So strategy is the state that they start with, and however they locally change it. So at the end, they end up with a new quantum state, rho prime, that of course depends on X because it's a question that they got. So what is the check that you have to perform to see if they won? So Px is going to be party X. So Alice if X equals 0 and Bob if X equals 1. So you actually want to check that this, you just do a projection onto the maximum entangled state with the corresponding party X. And if you trace it, it's the probability of a successful outcome when you project. And then you just average over the two possibilities, either Alice or Bob, and you just divide it by 2. And that's the winning probability of the given strategy. So what is the winning probability of the game? We define it as the best that you can do, so the supremum over all possible strategies. So this omega star is going to be, okay, no matter what strategy they pick, like they can take any arbitrary quantum state initial, and they can do any arbitrary CPTP maps. So what's the best that they can do? Okay, and now I'm just going to extend it in a trivial way to more parties. And now instead of Alice and Bob, you're just going to expand this to k parties. So the state is going to be like shared among all the parties. And here, a referee is going to have a qubit of this state. And now, instead of just sending 0, 1, it's going to send one of the k numbers. And the party that is designated at the very end of the game has to end up with a maximum entangled state shared with a referee. Okay? So that would be the goal. If it's like, now you are k people here, and I just at random select one of you, and at the end of the game, you and I are going to share a maximum entangled state. If we do so, you win the game. Otherwise, I win as a referee. Okay, so we have the first theorem that we can characterize what's the best probability. So for every number of players, so like, I don't know, let's say we have 50 people, so for 50, so the optimal winning probability is given by this kind of like beautiful expression. It's like a half plus something that decreases with the number of players, and eventually it converges to a half if the number of players like grows very high. Okay, so the intuition is that you might have heard that entanglement is not monogamous, in the sense that I said before that if you and I share maximum entangled state, you and him cannot share simultaneously maximum entangled state. So that goes as follows. I'm just gonna, for intuition, stop only for the case of two players and the referee. If like these two people are married or having an affair, lovers or whatsoever, so the other player is left alone. Okay, but on the other hand, if it's them two who are together or they're married or having an affair whatsoever, I'm sorry for the other guy, he has to be left alone. So that's what the monogamy of entanglement is in a nutshell. And that's why actually you cannot win this game with probability 1. So actually if you have two players, that would be 3/4. Okay? And the optimal strategy, we just like, we give what is the value, but also what is the strategy that attains it, is just by preparing the initial state raw, pure state, like this one that they do here. And actually they don't act depending on X. It is essentially if all of you guys were preparing for being ready for sharing the maximum entangled state with me, no matter what is the question. And then if it's not you, you trace it out and you trash it. So it would be to have the maximum entangled state, the referee and Alice, and some trash on Bob. And you kind of symmetrize this thing. So now you would have the referee and Bob maximum entangled state, and then Alice. And then you normalize, and that's the best. That's an optimal strategy that achieves this value. And now you might think, okay, maybe you can think of other natural states that are like tripartite entangled. Maybe the GHZ state, that one performs significantly worse. And also if you look at pairwise, the entanglement, there's no such a thing. But also you can think maybe like the W state that has more pairwise entanglement, but also that performs significantly worse than the optimal value. Okay? Now I gave you like this theorem, I gave you the game with the optimal probability and how to attain it. So what's the more general case? So I said, you and I have to end up with a maximum entangled state, but we can just like, okay, whatever other state. With arbitrary dimensions of R and P, no need to be qubits. Okay, you just think of a general state with arbitrary Hilbert spaces R and P. Okay, so now this is the k-party quantum cloning game, but with a target state that is a different one than just the maximum entangled state. So for short, it's going to be capital psi quantum cloning game and the number of parties k. Okay, and then so we have the same picture as before, but now instead of a qubit space, we have an arbitrary space, and instead of an EPR, which is going to have like the state that you want the most. Okay? And then we have another theorem that the optimal winning probability, when you replace it for every number of parties and every state that you pick, is given by this scatter norm, the infinity norm of this guy. That actually, if you know the state, you can compute it. You can even put it in mathematics. It's the largest singular value of that matrix. But it's something that like it has a closed form. And actually, if you replace that by EPRs, you get the value that I showed you before for the EPR case. All right. Now I think that I have to go to the applications of this. I promised I was going to show you a new game and some properties. Oh, sorry, not the applications, the parallel repetition. So we had these two scenarios. So the game played with APRs and the play game with any other state. And then that's the comparison, recap of what I did so far. And now, okay, often enough, it's very interesting to play a game like many times to get some statistics out of it. And it is usually even more interesting to play it in a single execution so that you don't have to wait for like multiple rounds of the game and stuff, right? And that's what I'm going to do here. I'm going to analyze the quantum cloning game when you play it n times in parallel, which is the following. So you have the same scenarios before, like this picture. I apologize. I showed it many times, and I will still show them a bit. So now you have n qubits that are held by the referee. And now you pick a bit string. So you send all the bits, x1 to xn, to the players, and they have to end up with a final state that has to fulfill the following. If xi equals 0, so it has to be Alice that for this particular index has to end up with a maximum entangled state. And that has to happen for all the i's such that xi equals 0. And similarly for Bob, if xi equals 1, well, it has to be Bob that now has to end up with a maximum entangled state. And then like it also has to happen for all the i's such that this equals 1. And now the check is similar as before. Now you end up with this final state with the corresponding correct labels that are depending on the xi that they received. And now you just project onto this state here. And this state is just the tensor product of all the maximally entangled states. And now you trace, and you know the probability that that is a successful measurement. And now you average over all the exponential bit strings that you can have. And that's the winning probability. So what I'm going to show next is what is the best that you can do. But actually, we were not good enough to find a tight bound, but we could find an upper bound. So we have the following theorem that the optimal winning probability decays exponentially with the number of rounds that you play, and that's 0.85 to the power of n, which is exactly the same value as the CHSH game. And on the other hand, we know that it is lower bounded by this, which is like just playing the strategy that you have for one round. And I'm more inclined towards this value for being optimal, but we could improve it. So if you have ideas later on, I would be glad to talk about it. Okay, so now we have the theorem that if you play it many times, the value decays exponentially. All right, and now, as promised, I'll go to the application, quantum position verification. So assume that I just opened my phone, or maybe this is more like a tablet because it's bigger, and I get a message that pops up from an unknown user saying, hello, it's your bank, please make a transfer to this account. For the record, this is not my bank account. If you want to tip me later on, I'll give my real one. Just kidding. And then it's like, okay, I have some trust issues. Can you prove that you are the offices of my bank? That would be a way to certify that you're actually working there. Otherwise, it'd be a bit difficult to sneak inside of the whatever offices they have. And it's like, okay, of course, I send you my location, and I just get a WhatsApp with a location. All right, so how does this location thing work? GPS, triangularization, something like that. Usually you have like a prover that is at a certain location here in Bangalore. And now with satellites, they send messages and they communicate so that they intersect here, and then you have responses back. And by timing, how long it takes, so you can do a triangularization of the location, and you can certify that the location is there. Okay, I have to say that bad news for the current technology, but that can always be hacked. And here is where quantum plays a role. And that's good for us because as long as we can prove that quantum is better, we all can keep our jobs, I guess. All right, so I'm going to show a particular protocol of how to verify the location in one dimension. So that's in a line instead of the three-dimensional. That's easier for the schemes. And that was introduced almost 15 years ago now. So we have the prover that has to be in a line. And then we're going to put two verifiers that want to cooperate and then want to check if the prover is at the claim location. So the two verifiers are going to be placed on the left and on the right of the prover. And they're going to send verifier 0 and verifier 1. They're going to send messages at the speed of light so that for the very first time, both together arrive at the position P. So that means that if you have, well, that's a protocol that take a BB84 state, either 0, 1, plus or minus, and then a bit. So if you have the time arrow, what Alice would do is like you look at the light cone, and maybe you're familiar with the light cone, but like that's the region of the space-time that can be connected causally. So you cannot communicate from here to here because that would be communicating faster than the speed of light. So if you send a message at the speed of light from both sides, it intersects for the very first time at the position P. So that's what I did before with the circles expanding. So now they send information, so a quantum state, a BB84 state, and a bit. So the bit is going to say, okay, you got the state, you either send it left or right. So at the speed of light as well, you have to answer back. And if x equals 0, you have to send it to verifier 0. Otherwise, if x equals 1, you have to send it to verifier 1. Now let me clear this out a bit. So the protocol is as follows. The information is received both at the same time for the first time in the location P. If you're in the left, you would receive both here. If you're in the right, you would receive them there. So the only location that you can get both at the same time is at position P. If you are somewhere else, the intuition is that you cannot answer to the other people. Okay? And if the state arrives on time and to the correct verifier, we accept the location as good one. Okay? So make a decision, so you have to run the protocol a few times. So like 1, 2, 3, n, and then you accept if they are all correct. So that would be repeating it once and twice and thrice and so on. Okay? So, and now I'm going to briefly go to the purified version of the protocol. And essentially, I want to show that sending a random BB84 state, and here I'm going to skip the details, but is indistinguishable from preparing an EPR pair and sending half of it. If you have more questions about that, I'll explain them later, but it is exactly the same, but I want to skip this part because the next one is more interesting. But it's actually indistinguishable from sending a random BB84 state. So that means that the previous protocol where you had to send a random BB84 state can be changed by, instead of sending the information and having to answer, you have to send this information, but now it's half of an EPR pair. So you keep one half as a verifier, and you send another half to the prover. And if x equals 0, you have to broadcast, well, to send it back to the verifier. And if x equals 1, you have to send to the other verifier. So what happens now? That if x equals 0, here you have to have the maximal entangled state. If x equals 1, it has to be the other side. So now you might guess that this has the flavor of the game that I showed you before. And if instead of having a prover in the middle, you have two people that are attacking, and now I'm going to rush a bit, but essentially you end up with like intercepting the messages. And what really matters is that you can perform whatever operation on the initial state that they share. And I'm sorry for rushing this, but I want to finish, and I'm sure no, I'm a bit short in time. So at the very end, I want to show that an attack reduces to the cloning game. That actually, if x equals 0, has to be attacker Alice, who has to have the maximum entangled state with the referee, and otherwise it has to be attacker Pop. All right, so with that, we can show that this cannot be won with probability 1. So we have that, and this is like in a given attack model, that the probability of successfully breaking the protocol is 3/4. I have to say, though, that this model is necessary because if they share entanglement before the execution of the protocol, they can do a teleportation of this part of the state to the other side, and they can perfectly attack it, but that I will cover tomorrow in another talk that I'm going to talk about a similar protocol. Okay, so, and in the same way, that you have to repeat many rounds to verify the location, you can also execute all the rounds in parallel. And now, instead of having to send one state and then another one and then another one, you prepare all the states at once, you send them all, and from the other side, you send each of them if it has to be sent to the verifier in the left or verifier on the right. And then, like, actually, all the ones that have to be sent to the left have to go to verifier 0, and otherwise to the other verifier. And you actually accept the location if they all arrive at the same time and they are correct. So I want to stress out that for quantum position verification, executing it in parallel, it is quite important, because if you have to execute this sequentially, one round and then another one and then another one, and if you compare it to the other one, it takes longer time. So a prover has to be static during this time, whereas this takes much less time. And I know that there are like some applications that are recent of quantum position verification that they work as subroutines for all the protocols. And for practicality, it's more interesting to apply it sequentially in parallel than sequentially. And in the same way that I argued before, that the cloning game could be useful for an attack. So here I'm going to do the same reasoning, that you end up in the final stage having to play a quantum cloning game. If you cannot win the quantum cloning game, you cannot attack the protocol. And with that, like, immediately we apply the theorem that we showed before, and we show that the probability of attacking successfully, it is upper bounded by something that is exponentially decaying. And I'm going to skip one more application, but that's just a modification of this protocol, and go directly to the open questions. That's another site. Sorry, might have opened the wrong file. Okay, that's a bit embarrassing. Okay. I can blame the jet lag. Yeah, I think that without further explanations, I will end up in this slide and say that the probability of a successful attack in quantum position verification decays exponentially. Okay.
Time for one or two quick questions. Okay.
So in your parallel repetition, so you have the two bounds. You say you lean towards the first bound.
Yep.
There's a third option is that because when you say three-quarter, you think of the classical value of CHSH, but the classical the CHSH doesn't parallelize perfectly like classically. Something in the middle. So are there connections? Are there direct connections with CHSH? Could you like?
Yeah, not that I'm aware of. And the thing is that if you think of the classical value of this, that would be essentially trying to guess left or right, and that gives something below the three quarters. So that three quarters, I guess it has to have sort of a natural interpretation, because it's like, I guess, too nice of a number to just pump out of nowhere. And like, if you just take sort of the classical thing, which would be just sharing a maximum entangled state with one part and then tensor something else, that gives 5/8, which is below that. And I have some numerical things, and I'm working towards something that, like, for n equals 2, that makes me believe that that is three quarters. I still have to double check and something like that, but I'm more inclined towards that mostly. Yeah. Exactly. Yeah. Exactly. And also we tried some like entanglement and swapping operations and something like that, and we couldn't find something that was a bit beyond that. And yeah, that's why I'm more inclined towards like the three quarters. But I guess. Thank you.
Maybe one question. Right.
And the first game?
depending on the input x is equal to 0 or 1.
Yeah.
Once we establish the maximally entangled pair between whether Alice or not. So,
yeah.
Generalization possible as you are saying the intuition is coming from due to the monogamy.
Yeah, exactly. That otherwise you could be able to share something that is maximally entangled state like pairwise.
So this you are saying the intuition is coming from monogamy with some generalization of the task possible. That depending on the input, at least one to establish a extremal non-local correlation, let's say PR box kind of thing.
Yeah, but like PR boxes are weird here because they are just probabilities. So they are like. Yeah. Yeah, but the thing is that like non-signal boxes they use for like seeing correlations with classical outcomes, but here the outcomes are quantum states. So I don't know if there's like such a generalization, but it would be nice to see, but because usually those things are easier to analyze mathematically, because the non-signal thing you can always find it with a linear program, and exactly it has like a very well-defined structure. So maybe if we can just define an analog of that for a quantum and then show that but I don't know how, because like you do it like just depending on the correlations, so that the probabilities of the outputs are like if you change one of the other's inputs, it doesn't vary, the local ones. So I don't know if we can do that in this way, but we can just like think of it and have a look. Why not trying? Yeah, sorry.
Thank you, Master. I just had a quick question, maybe it's just a clarification on my own, but you said 58 birthday for the record.
Well, not useful, not, but like it doesn't perform as well. Yeah.
If I'm not mistaken, if say Alex Bob reshares his state and Alex makes it in the Hamilton state, then regardless of the outcome, then directly and share a maximum kind of state in that case. I was wondering why that's excluded from the
It's 5 plus or 5 minus.
Yeah.
So you get okay, the upside the way you go plus or minus. Yeah. So that's
Yeah, can. Yep. Like more question?
Yes, I was wondering about this learning with this. Two questions with the issue. First of all, do you as if the referee has a larger system that is the qubit, which is many qubits together?
For what?
Parallel repetition, do you equipment game to say you have a larger dimension for your.
No, because it's like then you have two options with a full state that has to be either one party or the other one.
Many times in parallel.
Yeah.
And we're looking at the larger state and then sharing the relation.
No, but the state then it changes the one that you check later on, because it changes like the registers that you have. I can explain you now.